Well, I wasn't invited if there was one, and that would make sense, you know.
Here you have a reputation.
Yeah, but you have contributed to this reputation.
Oh, it's still not 11.
Yeah, there's 2 more minutes to it.
It might have seemed to have.
Yeah, that's. They decided to flee the building.
Crank up the volume there, we can get this natural echo.
Hello.
All the way through the tour. Maybe get a feedback as well, that's even better.
And maybe you can get a ring down.
Yeah, we might even detect it. So I think the general conclusion is that if we after this week find that we won't detect anything useful, we just cancel the rest, right? So come back for the R process and neutrinos stuff. Because at least we've seen how many neutrinos. Neutron stars.
I guess the focus of this week was on waveforms, so are
Who
this
said that?
I saw it
I think
somewhere.
no one said this week was on waveforms. That's far too detailed. I think this week was in more gravitational waves. Next week was in numerical relativity, not just waveforms.
Right. Gravitational waves, including what they happen to look like.
Turn that light off. It's right behind you.
Just done.
Okay, so Jocelyn will tell us about matter effects on waveforms.
What an introduction. Absolutely beautiful.
Hey.
Even the title is not
Well, I mean, before the merger, actually. So that's different than some of the waveform things. Yeah, it's another line. I know that can be tricky. So yes, well, thank you all for showing up today. I tried to do 2 kind of things in this talk. I tried to make it somewhat accessible for people who aren't totally familiar with this, and then I also tried to respond to various discussions and comments and things I've seen in the first few days. So that means I probably made it sort of too technical in some places and maybe kind of replicating previous stuff in other places. So just don't ask questions about stuff that bores you. We'll get through those parts quickly, and we can spend more time on whatever people want to discuss more generally. So anyway, since I'm focusing on how we have some impact of matter, equation of state, before the merger, we're going to be focused for this talk basically on the cold equation of state. So we have a 1-parameter family, pressure versus density, and these happen to be the some sort of I guess. Example equations of state that I use later for some of the work that I'll talk about. But just as a reference, so we have kind of a set of 3 relatively realistic between something like 10.5 and 11.5 kilometer radii for a typical neutron star mass. And then I also have this one, which is a somewhat unrealistic kind of 15 kilometer radius neutron star. But it's easiest to see the effects of that one, so it's a nice kind of calibration for if we're going to be resolving matter effects, we can resolve them much more easily in a large star than a small star, so that's sort of a extreme case that's still, I think, useful to see how it behaves. But a lot of the time, if I'm talking about sort of differences that are maybe more meaningful for nuclear physics people, it would be the differences between equations of state in this kind of range of typical pressures, which are giving you this sort of canonical roundabout 11 11 kilometer radius. Okay. So jumping right in, I guess we've seen. Yes?
Just explain what those curves actually are, because they have some made-up equation of state, right?
Yeah, these happen to be the piecewise polytropes. The little dots underneath are.
Is there a reason why they're labeled like pencils?
The soft ones. The soft ones are labeled like soft pencils. The hard ones are labeled like hard pencils. Jolyon thought it was funny. So, yes, that is actually the motivation. And 2B won't come back because it was very hard to simulate, and actually it doesn't reach 2 solar masses anyway, so we can just forget about that one. Okay.
Why is very hard to simulate?
Compact neutron stars are typically harder to resolve. Why? Well, I'm maybe not the best person to answer that, but my understanding is just the change in density with the density gradients are much sharper if it's more compact. So, for example, trying to resolve the very sharp fall off is less, and you just have to have more points per kilometer to cover the profile of a star that is more compact than a larger star.
They're more expensive to calculate.
Yeah, and we'll see this later in some code comparison stuff.
Okay, but on the other hand, we don't have much
Yeah, but apparently that's fine. So I'll show you.
okay.
I can show you explicitly the resolution required to get small phase evolution differences is lower resolution for larger neutron stars. Okay, so for any kind of gravitational interaction, we're going to want to characterize how the star responds in terms of the effect on the gravitational potential. So that's why we talk about this lambda parameter, or there are also similar parameters for tidal polarizability or deformability is what I happen to start calling it. So this is something that's going to talk about the effect on the gravitational potential, the quadrupole deformation that produces a gravitational potential change. So it's more dependent on the high mass or typical mass than, say, the very outer layers, compared to the strength of the external tidal field. So this means, for example, it's not the same thing as the deformation of the outer surface layers at a given tidal potential. So this is specifically the characteristic you want to use for gravitational interactions. So just this ratio comes in, it generally depends as radius to the 5th power, that's the dominant effect, and then there's some love number that scales that somewhat. When you put it into the waveform, it works nicely as a dimensionless form where you just scale out r over m in gravitational units where g equals c equals 1. And then you have a nice dimensionless parameter and you don't need to worry about what you're measuring things in, so that's kind of nice. But just like you have radius as a function of mass, you can consider this tidal deformability as a function of mass. And the pattern is very similar to the radius. So large radius is going to give you large deformability. But this is just a function that you can calculate from the cold equation of state. So we've talked about this again before, but so this will have some effects on a gravitational waveform in 2 aspects. So there's 2 pieces. The main contribution to changing the waveform is that some of the energy is going into deforming the star. That's an extra energy loss from the orbit that adds on to the energy loss to gravitational radiation. So that tends to accelerate the end spiral of the 2 stars. They also have tidal bulges that trace each other's orbits that are coherent with the quadrupole moment of the system orbiting each other, so that actually amplifies the gravitational radiation a little bit. So you can work through this as a Newtonian calculation of the tidal interaction, but it comes into the waveform formally at 5p in order and higher. So 5 and 6 PN and also like octupole contributions have been calculated. So this will just shift the merger to earlier times, most dramatically, of course, for, say, this 15-kilometer radius star. But in a way that can be predicted in this perturbative method from the equation of state. So I'll come back to this in a few places, but so 5PN terms are a little concerning because there are unknown 5PN contributions to the point particle dynamics. So they have the same frequency dependence, but they are currently unknown for arbitrary mass ratios. However, there's some idea that these contributions from the tidal corrections can be comparable or larger to the point particle corrections, that we can estimate the size by sort of extrapolating from the way the post-Newtonian coefficients look at as they increased as you go to higher order. And you can also look at the test mass limit. So this is a mass ratio of infinity where these are known coefficients. So the coefficient numerically works out to be something on the order of 1200 in the test mass limit. But as long as you're in the sort of 1.3 to 1.4 solar mass neutron star range, a 13-kilometer star will give you a substantially larger coefficient, and so on as you go up in size. So certainly if you're trying to distinguish between things, you are currently worried about some unknown coefficient about this magnitude. So I'll come back to some of the ways to get around that. One useless way to get around that is that the point particle coefficients are constants, and as you can see, the tidal coefficients depend on mass. So if you happen to measure a mass dependence of an effective 5PN term, which is what you do whenever you measure lambda, you would know that this is not some unusually high point particle contribution. Unfortunately, with advanced LIGO, it looks like you can't measure any mass dependence of the higher order PN term. Plus, this whole story is pretty much obscured once you get into the numerical picture anyway. But there are theoretical differences in how these coefficients behave that allow them to be sort of in principle distinguished with perfect detectors and things like that. Okay.
What do you mean it's obscured in numerical picture?
So if you look at the Del Pozo et al. Result that we've seen a few times, so this is the combination of many measurements to find the effective 5PN term, one of the things they did was they characterized, in a way that sort of ends up looking like this, both the magnitude of the term and its dependence on mass. And they find that they can measure sort of the typical magnitude, but they put very weak to no constraint on the slope of lambda as a function of m. So this is coming from lambda as a function of m, and pretty much. So you wouldn't measure that.
So that statement you tried at about PP coefficients don't depend on mass. They depend on mass ratio. Is that what it means? That mu depends on mu?
Yes, so they do depend on nu.
No, but that's right. But it's something more than that, because things like tail terms depend on the total mass of the system. It's true. I don't know what happens at later parts, because the scattering of gravitational waves depends on the total mass of the system.
Yeah, so if you start putting these logarithmic terms into the PN, and you can plot instead, say, each correction to dx dt, they still look almost entirely linear until very high post-Newtonian coefficient. So for any neutron star in spiral, that logarithmic term should have very... Yeah, so you plot them, they still look like straight lines until you get to very high x. So effectively, they are constant for the region where you would have a binary neutron star in spiral.
Because I was just asking that question as a matter of principle. Depend on the...
Yeah. So
We now worry quite a lot about whether we can actually determine the mass term. I think it's psi in the Fourier coefficients. It's psi 5 or psi 6, and there's something called psi ln psi 6, and that can be measured. And would that be helpful? I mean, is that
measured in what?
Using just the post-Newtonian coefficients.
Yeah.
I will talk to you.
Okay, yeah.
Because it's very technical. It may
Yeah.
not be very interesting.
Yeah.
So,
So.
Not just in post-Newtonian.
Yeah, yeah.
function.
Can I
Depending
ask
on-
another
Yeah.
question there? I know the self-forward people
Uh-huh.
are obviously very keen on comparing the numerical relativity, etc., to prove their worth. And
Yes.
so the trick there is to use the symmetric type mass ratio instead of the
Yes.
pointer. So could you not make some progress towards
Yeah.
by that?
Well, yeah, yeah.
Because if you know that, you can sort of, I mean, provided you assume that actually.
Yeah, so you could assume that you, especially for the, well, so for the, if you reparameterize in terms of this eta parameter, which ranges from 0 to 0.25 over the different mass ranges, it turns out that the self-force calculation is a pretty good prediction. So that actually gives you prior information that not only is this probably on the order because this is what the extrapolated scale is, but it probably is this to within some eta shifting. So so you could do better in terms of reducing the systematics by putting that kind of information into your analysis. There's self-force calculations where they calculate different Pn terms in the self-force calculation, and they take they take a self-force calculation which is perturbative, and then they expand in Pn orders.
So the idea goes back a long time. It goes back to black hole collisions, right? Where people found that if you take a point particle falling into a black hole and you rescale the mass, you take the small mass ratio and you rescale that as a symmetric mass ratio, just change it for no particular reason other than you fancy changing it, then you get a very close, the result is very close to what you get from seeing full nonlinear simulations. Okay? And what they're doing here is the same. They do the gravitational radiation reaction for a small body around a large black hole, and then you rescale the results, which are now more or less analytical, the same way.
Mm-hmm.
And compared to numerical relativity at higher end, it seems to perform pretty well as well. So that was the question.
Yeah. So we do have information about these unknown terms from these limits and things like that. So you could. So also as another caveat, I haven't. There's also unknown 4 and 4.5 Pn terms, which can be larger than the 5 Pn term in the relevant range. But again, there's some information you can use if you were really concerned about this sort of systematic effect.
Can you also use EOB to extract
So yeah, you can put effective higher order terms to EOB and calibrate it.
Ironically,
but
EOB needs to fix 3 parameters that you will fix the same way that I just said. So I think that goes back to the.
Yeah.
I mean,
So part of what EOB
anyway.
part of what EOB does is use these self-force things.
So essentially
So-
the same.
Yeah.
Yeah.
Once you've done it, the EOB description is probably more effective.
Yeah. Okay. Okay. So let me sort of say a little bit about how this plays into measurement. So here's my cartoon of detecting a gravitational wave. So I have waveform space here. I've made it 2-dimensional because infinite dimensions are kind of hard to visualize. No signal is that little cross, and then here's my family of signals, this 1-parameter line of possible waveforms that could be produced by some astrophysical system. So here is the signal produced by our system. Some noise in the detector buffets it around in this space. We measure something over here with some uncertainty characterized by the noise that we can also estimate by looking at the state of the data at that time. So we have some measured loudness, which for measurement, because of searching over many times, typically this needs to be a signal to noise ratio that is large, so not just sort of 1 noise step away. You want something that's around 8 noise steps away. Yeah, so I have this slide because sometimes people ask me this. So for this whole detection procedure, uncertainties in the equation of state have pretty much no effect. So it does not matter for that. You can actually see this more sort of with a full calculation. For example, if you restrict the analysis in broadband or advanced LIGO to below 400 or 450 hertz, you get small reduction in SNR, and you show that the tidal effects have no contribution. So for example, there's this paper that Ben and I and Tanya Hinderer and Ryan Lang did some time ago, where we showed in sort of the advanced LIGO mass range, this purple curve is this is what you could see with advanced LIGO from the point particle correction, the tidal corrections below 450 hertz. This is a 15-kilometer star. So if you have 2 one solar mass stars that are 15 kilometers and they have a signal-to-noise ratio of 30, you might be able to tell them apart. But it's basically no effect for most reasonable parameters for the purposes of detection.
But if you increase the frequency range to higher frequency,
Yes, so this has no effect at all. If you increase it to high frequency range, you're going to get some, maybe, again, less than 3% reduction in SNR from imperfect modeling. So, okay, but we want to talk now about not necessarily just detecting the signal, but figuring out what the parameter that characterized it was. So going back to this picture, what we're doing sort of in this schematic idea is we want to find the closest parameterized signal to the detected point.
Do you want to use the laser pointer?
Oh, yeah, if there's a laser pointer, that was probably...
Center button. I think that is the one.
This is a laser pointer?
Yeah. The center button says laser.
Ah, cool. Okay, yeah, I can do that.
Jocelyn, can you just tell us the difference between those 2 noises again?
They're just centered on the true signal and the measured signal. So they have the same, so the noise in the detector has the same scale, the same size in this waveform space. It will push things around by some Gaussian distribution centered on the point with some scale.
But in terms of like reality, it's the same noise? I mean like instrument noise, LIGO noise?
Yeah,
Oh.
yeah. Yeah, so this is just showing how much the instrument noise would affect the measured parameters.
So it's got nothing to do with numerical noise or...
Yeah, so far this is just a detection measurement picture for the actual data analysis side of things.
And just so that the logic is consistent, a blue star can never be on the pole line, right?
Oh, it could.
But then you would have 0 noise?
Yeah, if you could happen to have the configuration of the detector that did not, I mean, that was very close. By chance, it happened to be,
By chance.
yeah. So you have a Gaussian, okay, maybe not Gaussian, you have a Gaussian-ish, or after various, okay. Eventually you have some noise that's characterized by, it will change your measured parameters by something that has some distribution with some characteristic amount that it can change parameters. And when you calculate this metric, well, I'll get it, but basically it's going to push you around some amount. You're going to measure something which could be anywhere in this sort of area with some probabilities farther away, and then you extract parameters that are not exactly the true parameters, but you can estimate from your knowledge of the noise what the error in those parameters would be. Okay, so this is just purely from...
What space is this describing?
So this would be a waveform parameter space. So in reality, okay, I don't really have this. So this is the space where I should have kept another slide. So if you define the inner product that you use for detection to define the signal to noise ratio, that inner product defines a length scale. And that length scale characterizes the distance between 2 points with different parameters. So you can think of the waveform space as something as like just the value of the Fourier transform at each frequency sample is an independent dimension.
So every point here corresponds to some time series, data time series.
Yeah.
Some of which can be pure noise, and some of which could correspond to a signal with a certain lambda value.
Yeah.
And this line is that one dimension in this picture at least.
Yes.
One dimensional family of
Yes.
lambda parameterized signals.
Yes.
Okay.
Yeah. So just sort of a schematic view of how this is happening. So this is sort of slightly more detail. So we have something like the expected SNR of a signal. We define with this noise-weighted inner product that gives you a distance in the parameter space. Okay, so that's this distance that I've plotted based on noise versus itself gives you a characteristic scale of 1. So this gives you the signal to noise ratio, the ratio of the distance of the waveform from 0 to the characteristic size of the noise. So there's this measure that is used then is to look at the difference between two waveforms and then calculate the signal to noise ratio, the expected amplitude of that difference in the detector noise. This is something that gives you what's called marginally distinguishable waveforms. So the difference between the waveforms is comparable to the expected scale of the noise. So there's various people that have worked this out in more detail. But then the idea is that the expected measurement uncertainty for a single parameter is something like the difference between parameters that gives you this marginally distinguishable waveform. And now if you're in a limit where you can linearize around the parameter value, so you can linearize around your parameter family, then you can talk about your second waveform being the first waveform plus some linear contribution from the changing parameter value. This is basically the basis of a Fisher matrix approximation. So this delta lambda of marginally distinguishable waveforms is equal to the Fisher matrix estimate of a 1 sigma error. But it's just not doing this particular linearization step, which will be important for some of these borderline cases I'll talk about later. Okay.
That lambda
Mhm.
bracket one?
Huh?
That the lambda with bracket one doesn't take into account the correlation between other parameters.
Right, so
It's not the same as Fisher matrix system.
yeah, so that's the single parameter
Oh.
family kind of limit. And you can do more, you can do an equivalent multi-parameter breakdown in this setting as well as in the Fisher matrix setting to see kind of correlations in multiple parameter things. But that's basically what turns into the effective Fisher matrix in that formalism. Okay, so I talked about if you cut things off at 400 hertz or so, you don't see anything. If you extend, say, this post-Newtonian model to merger, you get something that says that the tides are measurable and have small effects on other parameter estimations. Okay, so this is a result from De Moor, Nagar, and Villain. So they argue in this paper that the P and tidal effects they calculate have the same magnitude as tidal additions to EOB, which is their preferred model. So they actually do this calculation with the post-Newtonian model with tidal corrections added to it. So that's a Pn plus tidal in spiral, extend the higher frequency up to the estimate of the contact frequency. And this does this, they do a full Fisher matrix parameter estimation with mass, spin, all the parameters correlating with each other. And the upshot is that with these polarizability parameters that they use, they get these values for the tidal parameters, and at rho equals 16, so at half the distance of your horizon, you get some 1 sigma measurement errors that are comparable or smaller to the typical parameters of the equations of state. Okay, so this is.
Sorry, may I ask, is there an easy way to compare this to the plot from the Hinderer paper? Because this is different units and different.
Yeah,
It's just different units, right?
It's basically, this is a different unit scale. That's basically the difference.
Okay.
So if you take the Hinderer et al. Paper, we have a formula in there where you can extrapolate to higher frequencies, and you get something that basically agrees with this. They have some higher order tidal corrections in it, and then they marginalize over other things, which actually we did too. So this is actually compatible with the Hinderer et al. Paper, assuming you just extrapolate up to contact frequency. Okay, so why is going to high frequency so important? You can also see in this nice plot from that paper, if you look at the frequency dependence of where the information of the waveform is coming from, you find that the mass parameters, these two peaks, and the total signal to noise ratio are typically accumulated here is as sort of a 55 hertz. Okay, so this is where you learn about the masses from the low frequency part of the signal. The tidal contributions come in at the high frequency part of the scale. These are all normalized, so there's lots more information in these pieces than this piece, but this sort of shows you how if you stop at around 450 hertz, you get very little possible tidal contribution. Whereas if you continue to the contact frequency, the information in the waveform that tells you about tidal contributions is rising. So you want to go, the game is to go as high frequency as possible to get the most information out. That is where half the information half the SNR of the 1.35 solar mass binary neutron star has been accumulated. Half the SNR, yeah. Okay. So one thing you want to worry about is your waveform family is not necessarily something that can be easily linearized. Okay, so Fisher matrix estimates in something where the noise scale is comparable to the separation in the parameters, so this is basically the low SNR limit, the Fisher matrix can break down. So for example, you can have some change. Let's see, so a weaker signal, something farther away, just means that the noise scale is amplified compared to your waveform scale. So this would be something that's twice as far away, has twice the noise relative to the waveform family, but the distinguishability of two parameters doesn't necessarily scale linearly in this complicated way. So this is why you don't want to rely on Fisher matrix estimates for these kind of borderline cases. But we have a bunch of results recently where people have done full sort of Bayesian style parameter estimations of this. This is something that Ben Lackey worked on with Les Wade at UWM. They have effective parameters of a binary, radius, and mass, chirp radius. So these are just sort of combined mass and combined radius parameters, and get some 1 sigma error ellipses, which for sort of the, I think this is 1.2 maybe, you have sort of this plus or minus 1 kilometer with the full parameter estimation. So things seem sort of consistent with Fisher matrix estimates, actually. Maybe a little worse, but not dramatically so.
Can you clarify whether these sources were similar SNRs or similar distances or RLH?
These are signals with SNRs of 32. So that's a sort of 100 megaparsec optimally oriented injection.
think what, instead of assuming, oh, they all give the same SNR? I think if you change the chirp mass, right, to higher values at the same distance, you should have greater signalization, especially when you go from 1.2 to 2.
Yeah.
1.8.
Well, this is chirp mass, so how does this work?
Those like chirp mass are 5/6.
Yeah, but so this is actually, if I remember how chirp mass, this is it's not a intuitively obvious mapping, at least not yet for me, between what the chirp mass is and what the individual component masses are. But yeah, so maybe if you fix distance instead, this top one would be narrower.
Exactly.
Yeah.
Yeah.
Yeah, that's quite. Yes. Okay, and there's this other result that we've also seen, combining multiple events and showing some sort of confidence around the characteristic tidal deformability of a 1.4 solar mass neutron star. They measure the mass parameters and this expanded thing for a population that has varying masses. And again, there's post-Newtonian end spirals and tidal corrections going up to basically the contact, or the ISCO actually in this case. Okay, so taking a post-Newtonian model, extrapolating it up. And Ben talked about a comparable study which looked directly at the equation of state implications of this kind of analysis. Okay. So that's, I guess, stuff we've all seen before. So again, like we've mentioned, so there's systematic errors that are significant for using these kind of post-Newtonian models. So Ken has done some stuff looking at the relative size of the systematic errors to the statistical errors from ignoring post-Newtonian terms of various order. So we have, I guess this is, the two are the same size. And for most of the mass range for advanced LIGO and for sort of a SLY equation of state, which is, you're going to have, most of the time, the systematic error is going to be larger than the statistical error from these kind of calculations. So this systematic error, that Ben also talked about, is comparable or larger. This is another calculation ignoring high P in terms of test mass size. And for advanced LIGO, you get the test mass terms contribute about the same amount in systematic error as you have in statistical error on measuring lambda parameters. As we said, we do have some information about what these terms are. So for example, we do know the test mass limit. So these systematic errors are conservative bounds on the systematic uncertainties. But in any of the results that we could do today, we would have to state systematic uncertainties comparable to our statistical uncertainties to make these kind of constraints. Okay, so one of the ways around that, of course, is to additionally use information not only from the test mass limit from numerical simulations. And this also can give you, so those systematics are just looking at these analytic calculations. There are contributions of neutron star interactions that are inaccessible to the analytic calculations that we've talked about so far, which could also produce systematics if you just naively use a post-Newtonian or EOB-based template that has no input from numerical simulation. So this is important, again, if you want to reduce the systematics as much as possible. I'm just going to flash through a few results in the last couple years have come out where we have fairly accurate simulations. So this is from Sebastiano's group, so you can ask him for any more details. There's the group in Kyoto, Kenta Hotakazaka led this particular paper looking at the contributions in the end spiral. David Radice, I think at the AEI, did another nice high resolution thing, comparing at very high accuracy phase differences in a numerical simulation to different EOB and post-Newtonian models with and without tidal corrections. So this is my interpretation, which may not be universal, of what things are generally, the picture of what things are in the state that they're in right now, which is numerical simulations do not conflict with any PN or EOB model that include known tidal terms until shortly before the merger. So at around, for sort of 1.4, 1.4, 1.35, 1.35 at around 700 hertz, the numerical simulations depart from PN and EOB predictions with things that I've seen published. So this is sort of the last few orbits. You can't, we see differences from the current EOB and post-Newtonian models. The current simulations are not sufficiently accurate to precisely measure these tidal contributions. They just don't conflict with them. And sources who may or may not be in the audience, I'll just, conversations have suggested that some people are confident that EOB-based models with this sort of analytic EOS parameters put in will be able to reproduce BNS numerical spirals in something 5 years. This is probably not something that everyone will agree with, but the modeling of the merger, up to the merger for binary neutron stars is not something that's intractable, I think. Models are being developed and calibrated, and so certainly we have to see this play out in reality, but we have a prospect of fully incorporating numerical information into analytical models in sort of a 5-year timescale. So by the time you'd be wanting to do measurement with advanced LIGO.
Maybe that's the point where you want to inject the don't lie caveat.
Which?
Because if you have resonances with hydro modes in these stars through the LIGO range, even if they contribute very little, they might, I mean, I don't know, right? But in theory, they could add up enough to mess up this.
Well,
because certainly an EOB type model will never do that.
So,
It will not be able to.
so you can also look at Dong Lai's paper where he calculated the impact of those contributions on waveform parameter estimation. So certainly they're not going to be impacting this particular measurement any worse than they would impact other measurements.
That's kind of a way of trying to describe a situation as positive, where it could in fact destroy more than just this measurement.
Right,
So,
but
I mean,
he,
you're saying
okay.
It's not going to affect this measurement more than anything else, but
And he
take,
estimated how much they would
yeah,
expect everything else, and it's sort of a few percent error.
There's a big caveat on that as well, right? The big caveat on that is that these calculations of any kind of resonances has never been done for any actually realistic neutron star models, right? Nobody's actually done that. So whatever has been done, I agree,
Yeah.
seems pretty safe. But I think there is a caveat here that one might want to worry about.
Yeah. So,
low frequency resonance due to what?
Oh no. See, if you take so we can take the stuff that was done by David Tsang and Adam Yu on interface modes. In a real neutron star, you have interface modes that, due to the different composition changes, right? And there's going to be a fair few of them in the LIGO band, not just the one that you looked at, but several others, right? So depending on how the composition changes are, you could have features that might be. So this has not been done, so I can just say whatever I like, and you can answer whatever you like, and we can sort of leave it.
and I can say the interface mode was vastly undetectable in the phase evolution. So things maybe you could be very, very pessimistic and say that resonance modes. You could also, talk to the data analysis and say, well, we can put some effective resonance into our model that fits some jump in the phase at a given frequency and constrain, marginalize, whatever.
The thing I object to is, in principle, I object to the EOB strategy for anything where, other than maybe the binary and spiral where it's clean. Right? So if you start putting hydro in, EOB is just not going to be in business.
Well, we can talk about this then. Yes.
The previous one. So when you compare the numerical simulations, can you extract, what is the uncertainty in the coefficients? There are the order 4, 4.5, and the point particle contribution to the order 5. So yes, it's not very clear, but can you derive limits on what those coefficients are?
Yeah, so typically, let's just sort of take the error as in this case, the error between the highest resolution and the extrapolated waveform is comparable to the difference between point particle and tidal. So that's what I mean by, so we don't really have strong constraints. So these two curves here differ by a 5pn correction term. That's within the numerical error estimate that I sort of quickly get by looking at the highest resolution compared to the Richardson extrapolation. So error estimate,
I think you cannot
5pn
extract
thing.
the precise value of the
Yeah.
It's very hard. So you can see what's the difference between one waveform and the other, and argue that is due to 5pn order. You cannot extract the value of the coefficient.
That's what you mean with measure.
Yes, yeah, yeah.
Maybe, if you go back to that, yeah. So what we've shown here is that, this is just a matter of will. There is no technical impediment in doing this.
Yeah.
If you want a line which is smaller than the red, you just have to
Yeah,
construct it and
yeah.
you can produce it because we have a nice.
And there are improvements in sort of the modeling in the hydrodynamics that give 5 years and these errors are probably going to.
Well, even now, I think we can easily
Yeah.
get a smaller value than the red one.
So this is so I guess like all these errors are not something fundamentally unknowable, but a matter of kind of computational finite resources.
So suppose you were to extrapolate what the computational cost would be, not in money, but in time.
Yeah, it's not particularly hard. Once you have a very, high order code.
Yeah, no, I know.
then-
So
then-
we take this code.
Yes.
So how long would that run take you?
A month?
Okay, so
But
that's
no,
fine.
it's-
That's normal.
yeah.
That's a typical. Okay, so it's fine. So it's not.
It's a
well,
kind of,
yeah.
it's a kind of cost of doing a highly sophisticated macrophysics calculation
Yeah,
of
yeah.
the Boston.
For anything to sign, yeah. But like the advantage is you don't care about the post.
Exactly.
That's right. So okay.
It's just
Okay,
a
that's fine.
spiral, simple physics.
Yeah, that's fine.
polytrops.
That's fine.
Yeah.
But still, that is not enough to certain analysis.
So this is
Nobody has data to do certain kind of analysis.
like to measure the 5pn term or something like that.
Say so what I've tried, and also I know Alexander has tried channel data, for instance, to compute this Q omega curves. It's a way to do phasing.
So this is something comparable.
It's sample of it.
Yeah, so this is as a function of m omega, which is a dimensionless frequency. What is the change in the frequency? This is from the spec code for binary black holes, which are a lot easier to push to high frequency. So this is sort of one of these things where we can say, in this case, you can say more clearly what particular models are matching the numerical relativity simulation over 30 orbits up to merger. I mean, these are very busy, but the blue curve here is numerical relativity starting at sort of 32 orbits before merger, where there's some uncertainty in the change in frequency with frequency, basically, is what these are showing. But for example, this green curve underneath here is something that would be like the Taylor T4 3.5 post-Newtonian. These other curves are other post-Newtonian orders. It happens that the 3.5 post-Newtonian Taylor T4 choice, for arbitrary reasons, mimics the binary black holes very well. So in that sense, we do know more information than is just purely in the post-Newtonian expansions. You can also compare it to particular EOB models, which I don't know the details of these plots. And then you can go to higher and higher frequency, up to m omega of about 1 or 0.12. Everything at sort of the highest p in order we know agrees with the binary black holes. So we have something that functions with the effective point particle dynamics of binary black holes, that we have a good model for this equal mass case until about this m omega. Okay, so I'm going to refer to this later just to show you where neutron stars are actually departing from this binary black hole simulation earlier than the EOB and the post-Newtonian models are in this particular case. Okay, so matter effects are more important in that sense than these high-frequency underlying point particle dynamics. So I'm going to show, let's see, I have 10 minutes left. So I'll show sort of some results from this code. So this is, the key thing is this is a code comparison from a large group of people that includes two codes, the Sakura code developed at Kyoto and the Whiskey code developed at the AI and Luciano's group. Multiple resolutions, single alignment at one point of maximum amplitude, and these are all these curves overlaid with each other. Which is, the point is, with these comparisons, we actually have a pretty good handle on what the waveforms look like around the merger. Okay. So, and you can change the equation of state, and you see merger structures happening at high frequency. There's fewer of these. Here's one. We have lots of different, we have some with different initial conditions, initial starting separations. You see some of the lower resolution ones start to accumulate differences going away from the match point. But in general, we have sort of these last few orbits that agree between all the different codes, different resolutions, different, actually one of these is hot and one of these is cold. It has a thermal contribution, one doesn't. So these things are relatively under control.
Two different codes, but the same resolution?
Not exactly. So one, yeah, the solid line, this dot dashed.
Okay, let's see.
You try to find them.
No, but I worry about what is happening before. I don't care about, because,
Yeah. So I can, okay, here, I can show you, if you want. So here, wait. Okay. Can I just show you? Yeah. So if you want to get really detailed, you can look at this plot of, where are we? So phase differences as a function of, this is the match point. Here's the post-merger, way less under control. Here's the in-spiral. These are the two highest resolutions. They basically agree.
Okay. They agree.
These ones are lower resolutions. It's all in line with, I didn't do a formal convergence test, but this is relatively.
And the same is true there as well?
This, what? This is one of the examples that for a larger neutron star, the 15-kilometer radius, you get, for a different resolution, you get this better agreement with lower resolution. That's what I meant by it's easier to resolve large neutron stars.
To put it in context with the binary black holes, the spec you had 32 orbits or something like that. This is 106 orbits.
Yeah. Well, so this is 10 orbits.
But with the waveforms, you would use it without everything.
Yeah, but that one's actually zoomed in on just this last part, so it's about double what I had previously. So let me. Yeah. So it's about double 1, 2, 3, 4, 5. So it's about 10 orbits.
Okay, so
In the, yeah. You can start to see the differences accumulate, but it's not very exciting.
No, this is gravitational wave, right? So it's half
Yeah.
that, maybe number of orbits.
Yeah, so this shows 10 gravitational wave
Yeah, so
cycles.
5 orbits.
And then the simulations go double the length. Okay.
So if you were to put the phase difference on the previous plot with the binary black hole, you would see comparable rates?
I think these have higher errors than typical binary black holes. And these particular simulations are not state of the art. So this is more a parameter study for different equations of state, but checking for consistency over resolution in different codes.
I think what is impressive is that the post-merger is really well, but
Yeah, it's
irrespective of the resolution.
Yeah. Well, it certainly gets worse if I extend out. So I think I have a skip slide for that too. All right. Well, this for this one I happen to. So it starts out for the first couple cycles, it's pretty good, but they decohere for the whole.
Yeah, so, but it's the phase which is different.
Yeah. Yeah, these are all the frequencies. So this is the instantaneous gravitational frequency with time. They actually show very similar features, but there's just enough differences here. And the time to collapse can also be very different for these different resolutions.
What it means is we can use the factor features, but not the phasing.
Yeah. Yeah. Okay. Okay, so and then as we mentioned, the kind of weird thing is that this in-spiral parameter also works to do things like characterize the gravitational wave frequency at the peak amplitude. So this is the logarithmic plot that Sebastiano objected to, but it makes a nice straight line. So that's all the reason I had. So you can have this fairly simple empirical relationship between equation of state parameters and the frequency at which the waveform reaches its peak amplitude. And Sebastiano in his paper confirms, I think this dotted line is the plot, and then these are your independent simulations that also give the same merger characteristics. So the merger characteristics are fairly robustly understood and are fairly universal in this sense that they depend on a single equation of state parameter, but not the details of the individual equations of state. And it's the same parameter that characterizes the n-spiral to leading order. Okay, so we can anticipate a reasonably useful single parameter family of neutron star merger waveforms. Single parameter in equation of state. Here's spectra. So these are the, I'm sort of out of time, so maybe I'll just skip these. But they're the same things you've seen before. I made sounds.
I think you have time. I think, shall we go back to that?
Oh, sure. Okay. Yeah. So here's these. So one of the things you can see, I've plotted with a very nearly invisible dot here the merger frequency. So this would be, if you assume the entire thing is monotonic in frequency, this is the frequency where it is no longer in-spiraling and it is transitioned to the merger. Okay, so you can see that kind of happening. You see this 2 to 3 peaked merger. Oh, here's one with a prompt collapse. So here, you have the peak frequency of the peak amplitude frequency is here, but you don't have post-merger oscillations. You have collapse to a black hole, and it oscillates at basically the binary black hole ring down frequency, but with suppressed amplitude because matter has smeared things out from the two black holes hitting each other. So this is an example of a prompt collapse. And then we see this characteristic thing. So the 15-kilometer radius has peak at around slightly under 2,000 hertz in the post-merger, 3,000 for the, 11.5 or 12 or so. And
are these codes completely independent?
Absolutely.
Yeah. Independently.
These people have never talked to each other.
They're both BSSN though, right?
Yeah.
I know, I think, yeah. In terms of techniques,
They are similar. They are similar methods. Yeah.
I mean, one when you didn't download yours. Change the name.
Yeah.
It's all coming out now, each other. That's the way public does it.
So.
Can I ask a question about you talked about the peak frequency thing and you showed
Yeah.
those nice correlations, but is it not true that that would be very hard to actually detect?
Yeah, the correlation is the correlation. So why I point that out, not because I think that is something that can be measured, but it shows that the merger is being characterized by the same parameter. Yeah, you would not measure it directly, but you can measure the mergers and say you're constraining the in-spiral parameter, which is what I can show in a little.
On the other hand, the F1, which I think is just
This little dude here.
You mean F1?
Sorry. F1 is AKA F1 is just that would be measurable, and it's essentially the higher frequency translation of that.
Yeah, well, yeah. So
because
you
it
can
maintains the universality.
Yeah, I mean, I think the frequencies, you can kind of see they all kind of scale together with the characteristics size of the neutron stars involved. So probably you can make similar universality arguments for post-merger stuff. And I actually made sounds from two of these hybrids, so stitched onto a long thing. So you can actually hear the difference between the two, which is kind of cool. So, yeah. But yeah, so that's, whoops. So it just chirps at a lower frequency, which is actually audible. There's sort of a natural dividing point. The waveforms, they go up, they have a peak amplitude, then they have this sort of minimum. You can use the minimum as a natural windowing to divide pre and post merger, and this is the explicit difference you get between the end of the in-spiral, which is a little messy up here. We have different initial starting frequencies and things, but starts to be, again, different resolutions here, different equations of state, different codes. And then the post-merger alone looks something like this, which is, I mean, it's just all plotted on one code, so it's a little messy. But we can use this in-spiral characteristic difference, basically treat these as templates, and try and measure the merger without referencing any of the in-spiral stuff that we've talked about earlier. Okay, so this is a purely independent measure of equation of state effects that I've just argued is characterized by the same parameter, but does not take any post-Newtonian anything or any EOB or analytic modeling at all into account, just taking pure numerical templates.
I was curious, rho is 2.8 or something like that. Oh, only due to this.
Yeah, only these numerical templates. So certainly this is not something you use for detection, but you could use this for the kind of the optimal template thing that James talked about later for trying to measure parameters with different. So I guess this is comparable. You were using, I guess, 3 sigma, so this is 2.8 sigma. So again, if you would want to get, well, I'll show you sort of where this comes out. I won't talk about details, but the upshot is that you get sort of this detectable difference, so something that gives you a difference of 1, which is the 1 sigma difference at 100 megaparsec of about 300. If you want to be 1 sigma at 200 megaparsecs or 2 sigma at 100 megaparsecs, you actually have to go to a larger, this is this nonlinearity I briefly mentioned before. And what, oops, oh yeah, and sorry. You can also talk about systematic errors, which means that in our sort of waveform space, the model waveform family or 2 waveform families that you have may have a shortest distance between the measured waveform or the best fit waveform and the true waveform, which offsets the parameters. So you would get some systematic error from equal parameter values by your model waveform family doing something slightly different in the space. which you can estimate. Let me just draw your attention to the sort of upshot. This is a conservative estimate. The two may be in different directions in the space, but you can just compare the magnitude of the difference for a variant waveform of the same parameter value to the magnitude of the difference for waveforms of different parameter value, and that gives you, this is giving you sort of an estimate of the systematic error coming from different numerical simulation results. Which for the largest, again, so this is for a particular, not state-of-the-art resolutions, the largest difference between two waveforms that had the same parameter but different simulations gives you an estimated systematic error for with this numerical only thing is between 40, well, it doesn't scale with distance the way statistical errors do, but it's less than the statistical error in this particular case. And would be better with more accurate waveform modeling, which is entirely possible. So this is the criteria that gives you this systematic error is 0.1 to 0.3 radians of difference over the last 1,000 M. And this has been improved on since then. Okay, so the upshot would be sort of this 1 sigma difference would be distinguishable, distinguishing between, say, B and HB at 100 megaparsecs, distinguishing between this 15-kilometer one and something that was quite small at 200 megaparsecs. And you can sort of roll your own rates and stuff by comparing to the horizon distance here. So basically, sort of 10% of the signals give you something like this, 1% give you something like this, very roughly. Okay, and then of course you can combine information and do things like that too, which basically will probably, well, this gives you something that's similar to these post-Newtonian comparisons. I talked about that already. Okay, so we used T4, I used T4 for hybrids basically as an effective point particle waveform. One of the things to note though is that just putting the leading order tidal corrections in compared to our effective point particle dynamics does not give you the same departure that numerical simulations show. So it's insufficient, and just putting in effective higher PN terms does not work to push this to agree over here too. And I'll come back to that a little bit later, but you can do these sort of hybrids. One thing I'd like to point out is if you create hybrids, or if you use PN to PN comparisons, you don't want to compare the amplitudes on a spectrum to see if something is measurable. You want to look at the amplitudes of the differences between the waveforms. So taking the fiducial waveform H, which had sort of a 12-kilometer radius, if I recall correctly, comparing it to the 15-kilometer radius, they actually differ at typical frequencies that are low. Okay, this isn't something that's right at the kilohertz thing where the waveforms merge. The differences are below or before the merger. This is in-spiral differences that can be used.
Yeah, but this is not much surprising because, I mean, in self-analysis, we saw that if you start simulation early and you have parameters, there you already see the 2pn,
Yeah.
you already see that you need
Yeah.
the 2pn fraction of tidal correction.
Yeah.
So
Yeah. So this isn't necessarily surprising, but it's, people like to plot the different amplitudes, and that's not necessarily telling you how different two waveforms are. These, say, H and 2H, look like they have the exact same amplitude in this region of the spectrum. But there is actually, that's where they accumulate the most difference in their phase evolution. If you sort of accumulate the, if you're talking about detection.
Why is minus H not zero?
Oh, these are two numerical simulations of the same equation of state. That's just sort of an error estimate. You could also, there's also other differences. There's particular hybridization choices and things that are more systematics than I've shown.
what is the dependence on the
I don't have a plot for that. I have, let's see. So this was sort of the comparison. So let's see. The approximate hybridization error is comparable to the differences between two neighboring waveforms, I guess. So it would be, the hybrid error would be comparable to H minus HB if you with these non-optimal choices.
So then how can we trust be able to see these differences between?
No, but that is far
That will give you a, well, no, so
the H minus H was.
that's differences in numerical simulations. Hybridization error is
Higher? I thought
yeah,
it was
that's,
the same order.
no,
Okay.
the limit on this is, these are short numerical waveforms, so that is something that can be improved by longer, more accurate numerical waveforms. But with these things, with just changing the hybridization, you could get some significant changes.
Is there a way to marginalize over, including phase consistency in hybridization? Because you know that you can't trust the phase.
These are two, what do you mean you can't
Like-
trust the
like
phase?
By black hole waveforms, when you hybridize, you also make sure that the phase remain consistent, progresses consistently from the post-Newtonian.
Yeah, so hybridization error that I'm talking about is changing the hybridization window. They're all consistent evolutions.
Yeah, but we know we cannot trust the phase to be consistent across different families. So should we insist on the phase progression to be? I'm thinking if there is a way to hybridize waveforms without worrying too much about how the phase progresses from the post-Newtonian piece to the post-merger phase.
So you could try and do some incoherent addition of just the numerical only and then the PN only,
Yeah.
and combine it that way, or do marginalizing over some uncertainty in the phase at the hybridization. There are ways to deal with that, I think, but.
I think to make a reliable algorithm, you need this kind of.
That's
It's not.
sort of estimates that I've seen. And these are hybridized with 5 orbits. That's why the hybridization error is high.
Jocelyn, if you could wrap up.
Yes,
and
sorry.
continue discussing.
Yeah. So let me just sort of see where I wanted to be here. There you are. Okay. I'm pretty close to the end. Let me just skip to the Outlook slide. Okay. So this is sort of, we've talked about all the pieces here. So the tidal effects are large enough to be measurable with accurate waveforms, something on the order of plus or minus a kilometer with design sensitivity and the equivalent of 40 detections. That's consistent over pretty much everything that people have published. This is a robust thing under modeling choices and stuff like that. Systematic errors are currently large. They're currently comparable to statistical errors, but they don't swamp statistical errors. So, and none of the systematic errors are intractable. They're modeling uncertainties, but they can be addressed by there's no sort of fundamental limit on our modeling that we've hit yet. So, in the next 5 years, by the time you have advanced LIGO broadband sensitivity, systematic errors are quite possibly going to be less than statistical errors for this kind of system, assuming that everyone keeps working hard. And, maybe there's unexpected bombs, and so certainly if there's some weird resonance effects, then all bets are off. But eventually we're going to require some sort of phenomenology to effectively cover parameter space for this stuff, or choose appropriate reduced basis simulations if we want to get rid of, I do want to show one plot. This is where the differences between post-Newtonian models with full tidal corrections and hybrid models come up. So this is sort of the limitation of the current sort of Taylor T4 post-Newtonian dynamics, which match binary black holes. And this is leading and next to leading order tidal terms. They start giving you some differences that are going to be significant for, say, a 15-kilometer star around 700 hertz, and for more realistic stars, something around 1 kilohertz. So just to sort of say that you do want to use this numerical input for this piece of the analysis. And in which case, you want to start thinking about what simulations are going to be sufficient to cover that parameter space. So that's all.
Calibration. I understand why you might be asked to be on the calibration review for LIGO. Because what did you assume about calibration errors? How do they affect these results?
So
for the LIGO instruments?
Yeah, so for the stuff that I primarily worked on, I just took broadband sensitivity. I didn't consider calibration at all. So whatever your phase calibration uncertainty is probably going to give you some additional error. I'm not sure if, I think, Ben, do you know if your analysis incorporated calibration errors, or did the Del Pozo analysis? I mean, people are doing this sort of thing.
Del Pozo did,
yeah, they did. So, okay, so some people have started to do something which includes calibration errors.
There are a lot about phase errors.
Yeah.
And,
yeah, everything here is basically insensitive to amplitude errors. Unless Chris asks about redshift measurement and you want to try and constrain the redshift, which would give you a few percent in the mass, and that would be a few, that would feed into this constraint, because the tidal term does depend on mass. So you would have some redshifted lambda something. I don't know exactly how it worked. Anyway, so maybe you'd be worried about that if you were trying to measure distance and limit that, but you can't measure distance very well anyway because you don't know the inclination angle. Anyway, mostly we care about phase.
So do you think it would be better to have 8, 10 models, very long waveforms where we know in detail what are the things, or just you would prefer to have more models simulated from from many groups, eventually repeating the same for modeling both purposes?
So
there are 4 or 5 groups
yeah.
that can do this thing, right? And one could, in principle, think to split it by choice.
Yeah.
And put them together together.
Yeah, I mean,
we are going to waste a lot of computer time and a lot of time. So.
there's certainly, like, I've only talked about equal mass systems here. So unequal mass systems is another whole thing that would be a spin to, could start to affect things. So there's certainly lots of parameter space to explore.
But we cannot do all of it.
Yes. Yeah. So certainly I don't think the most effective thing to do is for every group to continue to reproduce the same parameter space that other groups are doing, because what we've seen is that it seems that the codes do give consistent results. Yeah, for 5 orbits. So yeah, maybe you do need some comparison for very long, very high accuracy. This 10 orbits. This comparison I showed was. So it's a hard question. I don't know if I can just give a short answer. Yeah.
Not doing anything.
So I just have a comment about universality and peaks. I don't want to be, categoric, but we looked carefully. Kentaro has spent a lot of time trying all sorts of possible combinations. We do not find any universality but for the first piece, F1. All the others have clear dependence on the mass. So F2 does, as we show in our paper, have a dependence both on the equational state and on the mass. And this is why I think because F1 is so close to Fp, and Fp is universal, that the two are related.
So I don't know that there is some, from very preliminary results, looking at unequal mass and changing mass simulations, and trying to calculate this merger frequency that's earlier. There, you do have to. You can't fit at least I couldn't seem to fit M omega, a mass-scaled merger frequency, only using the tidal parameter. I would need to use. So
instead of using your big lambda, you use my kappa t.
Yeah. So you add a mass scaling in this
Yes,
too.
they're not there, but I have also equal mass simulation on that one.
Okay.
So that includes the mass ratio. And of course the mass.
So this is a combination of this includes some sort of implicit mass information.
It does include the mass and the top and the mass ratio.
So and then this, are you going to talk about this maybe this afternoon or?
Not this. I just show the picture,
Mhm.
but I mainly talk about it.
Okay. So yeah.
Not much.
So that game is also for unequal mass. It's just
Yeah.
that I didn't have so
Yeah.
much.
But there's also these universality relationships for the F mode, are there not?
Yeah, but that's the point. The F2 shows a universality at a fixed mass.
But no, not in the bar mode, the fundamental mode of the neutron stars. There are universality relationships for that mode in the right scaled units, and that is what we.
What do you mean by universe? I guess
Yeah. So this is just means that these equations of state are basically arbitrary functions. But it turns out in many cases, you don't need an arbitrary number of parameters to characterize the physical characteristics of a neutron star. You can relate, say, this love number.
often just depend on the average density.
Yeah. So you can relate. You can relate. So you could have some effective universal thing where you only need to know one characteristic of the equation of state, and then you can predict the F mode, the moment of inertia, the tidal deformability with some appropriate scalings. But assuming that this highest peak is a fundamental bar mode of some appropriate mass, then that should, from other universality work that have shown universality style relations for that frequency, yeah.
So this is what I'm trying to say. We
Yeah.
have tried to look at how F2 scales with any quantity, and we looked, for instance, at R1.6. That's R1.6. For those who remember, is the
Yeah.
the
But doesn't that
mass.
imply a contradiction with existing results?
No.
No?
Existing results show that there is a tight correlation. This is what James was showing yesterday.
Mhm.
This tight correlation with the knee at a given mass. If you change mass, this relation changes, okay? And you will have to have a relation for different masses.
So I'm actually thinking more of the fitting formulas for the mode frequency itself, not in this.
Oh, this is
not
for
as seen.
isolated star.
Yeah.
Yes. Okay. Well, yeah, but they are logically similar, but we're talking about two different things here, right? This is.
So
Produce
yeah.
by upper mass neutron star, there would be the relation between the F mode of an isolated linearly perturbed star.
Yeah.
There, the relation is not very sensitive to equation state.
Yeah.
And of course, it's also a matter of what do you call the universal?
Yeah.
Where you stop with you saying, oh, the scattering here is so large.
Yeah. So.
If you think that peak is an echo of this one,
Yeah.
you should be able to reproduce this.
Yes, we do.
With
Yeah,
one
well-
parameter, not.
Yeah, we can reproduce this.
Jocelyn.
I've got one more.
Oh, yes, sorry.
Maybe. We're kind of done with that discussion. Just this is a very broad general question. Just do you know anything, many possibilities or any talks you've heard about matter effects observed in binary pulsars? So here we go with electromagnetic pulsar data.
Like moment
and-
of inertia measurement?
Yes, or whatever, any matter effect.
Uh,
I've seen talks saying we will know the equation of state from binary pulsars by this year, like 2020. or something.
Yeah,
Do you know anything about
I have not looked at the latest results. Do maybe?
X-ray observation, things like loft.
So I think systematic errors with trying to get from X-ray observations to neutron star radii.
But the moment of inertia
This is the moment
measurement.
of inertia,
No,
just looking
yeah,
at,
so Jim might.
Yeah.
I don't know any more about that too. Pulsar people.
Yeah, there was some subtlety that some spin stuff came in and at the same order and obscured it or something. I don't.
People talks have said we'll know this.
Yeah, I remember reading pretty optimistic, like when Ben and I did the Piecewise polystrops, we had a moment of inertia constraint kind of thing because we read some papers that said, yeah, that could totally constrain things, and
You'll get a constraint for one system.
yeah,
And,
yeah. But it's
what we need is several radii
Yeah.
to see if there's anything interesting.
Yeah. So I think, I don't know, I think I've still seen papers saying that it's possible, but I guess it's just been more problematic than originally expected. So but I haven't read the latest stuff in detail.
Okay, so from a nuclear physics perspective, it looks like there's this early time signal where the main issue is what can be done to help is the systematics can be improved if there's more effort on numerical, comparing numerical waveforms with this. And
With early, you mean the inspiral?
the inspiral, before matter effects become important, can be
Well, I mean,
pinned down.
you say the matter effects are important even in the inspiral, right? I mean, the type.
Yeah, so there's,
Absolutely, but there are
Yeah.
these terms that are not sensitive to matter effects, which are coming in at order 4 and 4.5, which are
Even at
source-
5, even 5.
even at 5 that don't
Five
depend
and
on
6.
anything to
Yeah.
do with matter,
but
that are the ones that one should constrain using numerical
Control.
relativity. And once you have that, you're going to decrease the errors. And after merger, it's nice to have something like FP, but I guess the amount of physics that can potentially impact a simple interpretation of that is now very big.
I guess that can be done, the point particle one can be done by using binary black hole simulations.
yeah,
Very effective.
yeah,
How do you think they are physically done? Every model.
yeah.
And then to translate the.
Okay, so, sorry, that's a good point. If we know the 4 and 4.5 terms already from, comparing to black hole simulations.
No, you won't specifically know them. But I think you can construct a model.
We know the
effectively
point particle
incorporates-
dynamics to an
You know the full
effectively to
We
that.
can reproduce effectively with an effective theory.
You don't know
parameterize
explicitly what they are.
coefficients.
So what you can do is not to a frequency domain EN approximate with this parameter. This you cannot have. Okay. What they have done.
I guess I'm missing that because as a
What
function
is-
of time, the velocity is changing, right? This
So you can-
expansion parameter is becoming more close to 1.
What people have done to fix these things is to use experimental code data
Yes.
and compare with their UV model and fix some parameter in the Hamiltonian of the UV that effectively that are formal for the end at the end. Okay? Then from
Not
this
just pi p, I mean, it's up to all orders, it just agrees with the numerator.
exactly, but they are not the coefficient, right? They don't
Yeah.
correspond. If you expand, they don't correspond. It's just
Yeah.
from the simulation you extract this number.
The point is, at the times when these very high order things become visible, the whole idea of a post-Newtonian expansion is kind of breaking down. But we do have an effective model that will model the dynamics of the system at those frequencies. It's just not quite, I think people are saying it's not really useful to keep thinking about it as P in orders at that point.
It
I
reproduces.
agree, but
Yeah.
so you can't compare simulations at very low velocities to actually extract where the expansion is meaningful. It's
Mhm.
not possible to do it because then you have to do many cycles and you just don't have the time to do it. Is that the complication?
No,
Why can't you compare the effective model, which is a clear expansion in velocities, with a numerical simulation at small velocity?
You can do it, but the effective model is a PN model at low frequency.
So there is no
Yeah,
doubt about
it
it.
reduces
works
down
By
to PN.
construction,
PN works
with a PN model.
large
Yeah.
separation.
we don't know what he means by low frequency.
Yeah.
It's
Yes.
very, go to very low frequencies, they all agree. All post-Newtonian approximations are the same.
Yeah.
I don't know what you mean by low frequency. If you mean low frequency, lower to compared to merger, but still very high.
Yeah, so this
post-Newtonian
is,
approximations don't
let's see,
agree.
so this is this sort of low frequency thing. All the different EOB and post-Newtonian and everything models are getting very close together, and the
Okay.
numerical error bars are getting relatively high,
So
so.
let me talk to all of you in private about it.
Yeah, yeah.
It must be a very stupid misunderstanding on my part. We should thank Jocelyn
Oh.
again. Okay, I guess we meet at 2:30 today? Yes. Okay.
I'm down.
So